When you drive a car, you rely upon the ability to speed up through use of the accelerator and slow down with the brakes. The brakes and the accelerator balance each other out and enable smooth and controlled operation of the car. Failure of either system or overactivity of either system could result in disaster. Our bodies operate on a similar system of checks and balances and rely heavily on what are called feedback loops. In a feedback loop, production of a signal eventually affects the levels of its own production. This idea may seem a bit complicated, so consider an everyday example. A man begins to gain weight. His weight gain makes him depressed, and out of depression, he begins to eat more food. Subsequently, he gains more weight, gets still more depressed, eats still more food, and gains even more weight. You get the idea. This is a classic example of a positive feedback loop. Weight gain is triggering even greater weight gain through a series of related steps. In this and every positive feedback loop, the presence of a given signal eventually leads to the increase of that same signal. Simple examples of positive feedback are common in our bodies. In nerve cells, for example, influx of small amounts of sodium triggers voltage-gated sodium channels to open up, which in turn allows even more sodium to enter the cell. Positive feedbacks are not the only type of feedback, though. The body relies, perhaps more heavily, on negative feedback. Regulation of insulin in the human body exemplifies a negative feedback loop. The presence of sugar in the blood, from having eaten an apple, for example, triggers an increase in insulin release. Insulin triggers glucose transporters to arrive at the cell membrane and begins to remove glucose from the blood. As glucose levels now fall, the signal to release insulin disappears and insulin release is stopped. In this and all negative feedback loops, the production of a given signal eventually leads to a decrease in that same signal. Now consider a more schematic example of a negative feedback loop for clarification. Imagine that A is a sensor for number 1. When levels of number 1 are low, A senses these levels and responds by making signal number 2. Signal number 2 in turn stimulates B to make signal number 1. A senses and responds to increase levels of number 1, and as a result cuts back on its own production of number 2, which therefore drives B to decrease its production of number 1. With levels of number 1 low again, A would sense and respond to this change. As a result, it would ramp up its production of number 2 and start the cycle all over again. In the human body, feedback loops are essential to maintaining homeostasis. Consider the way that your body regulates its temperature. If your temperature is too high, you begin to sweat. As the sweat evaporates, it helps to cool you down until eventually eliminating the need to sweat. If you get too cold, there is another feedback loop to help. Shivering warms you up by exercising your muscles until eventually you don't need to shiver anymore. Of course, these are not the only mechanisms to maintain steady body temperature, but they provide a convenient example of negative feedback in the human body. Like your car, your body needs checks and balances, an accelerator and a brake. Often, feedback loops, like the ones described here, provide this balance.